In the real world, always something happens that you're not in control of. I really admire people who can turn that around and say, if I cannot control it, maybe I can use it. Those people are very rare, but it's often those people who get the possibility to make a business out of it. Today on this podcast, I have had the opportunity to meet one of those guys. You really have to look forward to listen to Anders Noel Thomsen, who will present a pretty smart way of making metal work. I don't think you have seen it before. For me, it was pretty new, and I was amazed. So please follow this and enjoy the ride. Hi, Anders. Welcome to the podcast on Everyday Metallurgy.
Hi, Peter. Thank you for having me.
It's a pleasure to have you here. We have met several times. I have been censoring some of your students working on the subject of today, and I have been really inspired because I never thought of doing what you're doing. So now we have a cliffhanger. First, can you introduce yourself? Tell a little about your background, your educational background, and how you became the guy you are today.
Yes, I can try at least. There's a lot of different decisions leading up to that. I guess it started with knowing I wanted to be some kind of engineer, knowing it should be mechanical engineer. I like math, but not really enough to go pure math. So I said engineer. That's sort of like a middle road. I chose Aalborg because I wanted to do the whole project thing that just suits me. Like I want to be part of a project and create something together with others. After I did the bachelor in mechanical engineering, I realized that drawing and SolidWorks were not my favorite tasks. Instead, I liked what happened with the material. What were the constraints behind it? How could we change some of those? So I did my master in materials technology, and I really enjoyed those discussions about what happens if we do this, what's actually going on inside of it, how does that affect the parameters we're seeing, and trying to understand that bit. I knew I wanted to sort of explore that with a PhD if I could. And that's where I heard about this topic of laser forming.
Yeah, that's it. So what is laser forming? I have always have trouble. I remember when I went to the university myself, I took a class in welding. And it's always easy to make a welding on one side. But then if you have to weld on the other side afterwards, everything is like, it has moved. So it has always been annoying to me that materials are moving when you heat them up.
Yeah.
But it seems that you are not annoyed by that, but you are actually using it for a purpose.
Yes, exactly. So
what is this laser forming about?
Well, like you said, it's basically taking the thing we hate from welding and then actually using it to create our parts. So it's a thermal forming process where we don't have external forces. So in traditional ways, you think of something like thermal forming, you say, okay, we heat up our piece and then we smack it with something, a press or some other thing. Here, we don't do that. We simply heat it up, allow it to deform, and we do that continuously. It kind of looks like magic because we use a laser. We're basically just heating it up, and the part starts to magically deform before our eyes. Yeah. It goes a bit slower than that, but when we speed it up, at least that's what it looks like.
Okay. And how was that initiated? Who got that idea, and how did you start doing that?
It started with I think my supervisor was on a conference in Germany and saw some Germans had done it. And that's where they got their idea. And then it was part of a MADE project for a PhD student. They had done a few projects on it at Aalborg University with students. And then they couldn't find someone to actually start it up and say, that's what I want to do. And then I arrived later and said, well, that sounds interesting. Let's do that. And I remember my first plan being like, okay, I'll spend a little bit on the process control part, and then I can spend a lot of time on the material science of it. And then that's sort of shifted to a lot on process control, and I'm still waiting for time to focus on the material science of it. But I got a little bit in there.
Yeah. So what are the process parameters? How can you control it? It can be a little difficult to understand why does it work, and why are you able to control something that used to be annoying?
I think maybe we should take I have a small video here, and you can see actually what's going on, and then that'll help explain it, because it can be a bit difficult to actually understand what it is.
Yes.
So here, I don't know if you can see my screen.
Yes, it looks wonderful.
This is sped up, but essentially we have here a laser that we're controlling, where we can control the amount of heat we're putting into the part. So we can control what's the laser diameter, the laser power, and the velocity we're moving across. And this controls how much heat we're putting into the part. And that controls how much deformation we're putting into it each time. So in here you can see it looks, almost like magic.
Yes, it's just bending. You can barely see the laser.
You can maybe skim it. I don't know about the video quality. So by controlling the amount of heat and how fast we're putting the heat into it, we're creating these temperature differences inside the part, and that controls the directions it deforms, how much it deforms, and the type of deformation we get.
And are you able to shape any kind of materials?
No. So what we can do is we can do compression. So we can compress a material locally, and that means that there's a lot of shapes that will be extremely difficult to do. Like you can't a sink or something. At least your classical definition of a sink will be quite difficult to do.
Yeah.
But you can do V-bends are quite simple, and then you can also do these double curve shapes. And that's one of the advantages of having this free-forming approach, where we don't need tools and dies to make these shapes. Instead, we can just control the laser in a little bit different way, and suddenly we'll have a different shape altogether.
Yeah. And the power input, it doesn't seem as you use a lot of power to do that. Is that right?
No, you typically don't want to melt the material. You can, it'll increase efficiency, but you can also do it below melting temperature.
Yeah.
So,
but then you need some power to go into the material. When you put a laser on it, if you put a lot of power in, you get an oxide scale. Then it changes color. Then you have a different absorption compared to if you have a very nice, shiny steel surface. Are you able to control parameters like that?
That's what we're working on. There's a lot of things that goes into it, because when you start to heat it up, we need to heat it up multiple times and then allow it to cool down. But it goes fast and we can do it more efficiently if we don't allow the part to cool fully down in between. But the problem is absorption and such are also temperature dependent. So if we have a higher temperature, we'll also change the absorption rate. So there's a lot of different factors that goes into that, and a lot of these factors are complicated.
Mm-hmm. Yeah. The component you just showed, is that a real component, or was it just something you made for fun in the lab?
It was based on a ventilation cover we saw in one of the offices. We needed because it's part of this project flip at the university right now, where we're trying to combine different laser parameters. So if you have a laser, you can cut your part out, you can bend it with laser forming, and you can weld it together with something else. And if you want to, you can also engrave some stuff into it if that's something you want to do.
So a multidisciplinary process. It's a Kinder egg, 4-in-1.
Yeah, a Swiss Army knife, just big and with robots and lasers.
Yeah. When you do that, you might also have looked into some competing technologies that could do similar things. What are you competing against?
We're in. This is one of the slower processes. So it's for low volume production. It's for prototypes. I like to call it the 3D printing for sheet metal. So we're competing against other processes that exist in that sort of domain, which includes free forming, incremental forming, which is you basically have a point and you go down and then you twist it around on the surface and try to sort of create your deformation locally. With that, there is hydroforming, which is another option of creating certain shapes. There is rubber forming, where you can avoid one of the tools or the dies, but with a big rubber block instead. So some of these processes that focus on low volume production of sheet metal.
Yeah. And what are the advantages if we look into laser forming compared to the other?
One of the advantages is that you can combine it with cutting out your component quite simply. So you don't have to sort of cut out your component and then take it somewhere else. You can just cut it out and then start forming it directly. Another advantage is that you have a lot of control. You can really do some very, very precise fine tuning, because you can precisely control the power. You can precisely control where exactly are you putting it in and how much. So this means that you can use it for anything from microelectronics and up to the largest we've done is 20 millimeter thick steel components. Where you can very precisely and accurately make changes.
So are you also able to form not only in like the one you showed in one single bend? Can you also make it up and then down on the other side to make it like complex curvatures?
Yeah, of course. You can do as long as you can sort of compress it and access it. Is mostly the thing with laser forming. So if you want to heat it like this, then you need to flip it over mostly.
Okay.
At least that's the most common way to do it.
Yeah.
So you need some way to manipulate your part.
Yeah. Can you explain a little more on the technical part, going deeper into the theory of how it works, the thickness of the part? If you have a sheet that is, let's say, 3 millimeter, you put laser on one side, but why does it bend in that direction and not in the other direction?
That's a really good question, and also the heart of the process. So everything is based on temperature gradients. So when you put heat into the top surface, it's basically what the top surface then starts to heat up, and that causes the material on the top surface to expand. But because all of the surrounding material, that's still cold, or colder at least, so it resists this expansion. And so when something wants to expand and the rest resists it, something has to give at some point at least. And that happens in this heated area. And so when it cools down again, then suddenly you have this compressed area that wanted to expand but couldn't. So when that starts to cool down, it contracts, and it contracts more than it did originally. And that sort of forces the entire part to go upwards.
So you build in stresses below the level of deformation initially.
You build in stresses above the level of.
Yeah. Then when they are cooled down again, they are released in plastic deformation, you could say.
Yes.
Does the properties of the material change when you do that?
Yes, of course. Properties always change when you do something to a material.
Yeah.
So then there becomes some of the interesting parts, because you have a process where you have a component which is the thermal one. You also have a component which is the plastic work you're doing. And so they depend on where are you along the thickness, where are you along the position, also has an influence. I have a very cool video to show you right now, at least regards to this.
Yeah.
So it's one of those things where that heavily depends on what material you're using and how much you're actually doing to it. If I can show you here
So you get some deformation hardening when you do that. So the second time you run over, you don't get the same level of deformation, or do you have to place your laser just next to it?
You can do both. So you can offset your laser a little bit more, so you do get some work hardening again, depending on material, depends on how much you do. So you can place it next to it, in which case you'll deform some of it that doesn't have some work hardening, or you can also just go across in the same position again. And then keep on adding more deformation locally. We had an example where we tried to do a 3 millimeter thick part and just went over the same area, bent it upwards to 90 degrees, as narrowly as we could. It took a very long time, but in the end it was 4 millimeters across in the bend, simply because we compressed so much material into it. And that also meant we had to adjust some settings along the way to actually get it to continue progressing.
Because that when it gets thicker, then your deepness of your laser power has to be changed.
Yeah, so what works for a 3 millimeter part doesn't necessarily work for a 4 millimeter part, or at least as efficiently.
Put in more power.
You have to put in more heat, at least, and a little bit differently. So to answer your I have a video here that actually shows some of it.
Yeah.
So this is an experiment we did where we sort of tried to measure what happens along the path of the laser. So we have a plate here, and then we move the laser across, and then we measured it at different positions and superimposed these. And this is slowed down. So you can see here that the laser starts to move across. That's causing interference with our scanner. And so now what you can see here is that, I don't know if you can see my mouse.
Yeah.
Here it's starting to bend upwards. That's from what I just explained. But you also have what happens over here, where it's also starting to bend before it is heated with the laser. So there you have a different profile of what's going on. And that means that what the material is experiencing over here is different from what it's going to experience over here.
Yeah.
And so you can see that becomes even worse. So here also, while it's cooling down, it's going to have even more deformation going upwards. And then when you start to move in different directions, everything just becomes even more complicated. And even more interesting.
Do you also introduce grain growth in the surface?
Potentially. Again, not simple to answer. We do work at elevated temperatures. So we go up to just below the melting, which would mean that it should be easy to say, yes, we do have grain growth. But we're only there at a very, very, very short time. So maybe a fraction of a second, maybe a second at most above, maybe for normal steel, 800 degrees Celsius. So then the dynamics of it starts to play a role. So the question would be sometimes.
Yeah.
The answer would be sometimes, depending on everything.
Yeah, okay. So this is a process that is not industrialized yet. It's still in R&D level. But can you disclose how far you are and what are expectations? I know that you and a colleague has initiated a company that should bring this to the market. So
Yes.
what are the forecast from your perspective and that?
It's always interesting to ask a scientist because they have to be very optimistic, right? Say it'll work soon.
Yeah.
I think that's part of what drives you, forces you forward. So the solution is obviously right around the corner.
Yeah.
No, the idea is that we have some of the simpler parts working, and now we're trying to, within the next 1 to 2 years, we hope that the first sort of demo installations will be out at industry, and starting to see production at companies. And the reason for starting this the startup is that there needs to be some driver behind developing this technology so it's actually used by industry. My biggest fear is, after spending so much time on it, is that it ends up as a small report in some desk somewhere.
In the basement.
In the basement, right?
Yeah.
So it needs something that's sort of more sustainable in growing it forward, and that requires some private institution to drive that.
Yeah, that's also one of the reasons why I was so interested in talking to you, because I would also help bringing it out to a broader audience. Because I know that some of the followers of this podcast, they are very curious to learn more, and I'm sure they'll reach out to you afterwards to learn more about what it is you're doing and if that could be transferred into their products. But what is the business model, Anders? Is it will you produce parts on your equipment in Aalborg, or will you be a service center that will help others to install their own laser, or how do you see it work as a company?
So basically, the overall goal, based on the Danish market, which is what we've been trying this for, is to sell laser cells where you can do this in. So we have this very, very complicated process. We're trying to simplify it enough that it's basically plug and play. Okay. So because otherwise it would be necessary to have a big change at the companies to adapt this technology. So we want it to be similar to, well, here's your part, put it into the machine, press play, and then it handles a lot of the necessary calculations to start making these parts. And we deem that necessary. And based on the Danish companies, what they're interested in is buying equipment that can do this.
Yeah.
And not necessarily developing it themselves. I think that at some point we will also be making parts and components as part of demo projects and other stuff as necessary to be able to show that it works to people, to demonstrate that it works.
Yeah. So the alloys you have been working on so far are stainless, and have you also worked on low carbon steels?
We have done. We actually did a material or a study on what different materials we could bend. Just try to see, could we bend it to like 30 degrees. We had titanium, brass, aluminum, duplex, normal iron steel, normal steel, and stainless steel, and copper. And they all work well. Some of them require a bit more adjustments.
My guess was that copper would be very difficult because the heat is distributed so fast, so you don't get that gradient that you want.
Yes, there are some materials that are more difficult than others. We've also done some very high strength steels, and it's very difficult to get them to actually bend before they start to melt. Like you have a very, very small window there where you can actually get it to bend. So either you have to
like high alloy tool steels.
This was for armor plating.
Okay.
It was just a test, like to see was this a viable way to do it. And the results were you could do it. And then the question becomes, what happens to the material properties after you have done this? And we don't have that answer yet.
Okay. Then the big question: are you alone in the world doing this, or are there other universities, other development centers or companies? Where do you go to share information? Is there a conference on laser forming?
Unfortunately, there have been a few before my time. Obviously, there are other people working on this in the world. There are some. I went to visit the group in Liverpool who have done this for multiple years. There's also some in the US, some in India, and China, obviously, that are doing this work.
Yeah. But you don't go share information that regularly.
No, it's a very small group of people, and it's working in different directions of it. Some are very focused on the material side of it. Some are very focused on are very experimentally driven. We are very focused on the process control side of it. Like how do we want to be able to make sure we can make a part before it's interesting to see what will the material properties of the part be afterwards. Like if we can't make it, it doesn't matter what properties it will have. But if we can make it, then the properties will depend on what industry it's used for. Like there'll always be different requirements for different applications.
Then I asked before about the sizes. I said 3 millimeter because I think that's within the reach of what is possible. But where are the limitations seen from your perspective? Can you go to 50 millimeter thick plates, or what are the limits of the process in sizes?
I mean, it's based on laser forming is a sub-process of a process called line heating, which is basically use heat to deform metal. So if you switch from a laser to either an induction or a gas, then it's also easier to go up in thickness. We've done at the laser cell in Aalborg 20 millimeter thick construction steel.
Wow!
It works. It's very slow. It takes time, but it works. But I think anytime you want to deform 20 millimeter construction steel, you'll need to think carefully before starting. So in that sense, it was okay. Our biggest problem was actually defocusing the laser enough, so we couldn't go higher, and we didn't have enough power to actually increase it. So it was as low as we could go, as defocused as we could go, as high power as we could go, and then try with that. But it works. If you switch to gas, for example, that's one of the strategies, at least in Asia, to how they build ships.
So when you bend and you want to have these curvatures before welding, I have seen somebody standing with a gas burner, just heating it to make it bend in, and then they could put the welding on.
Yeah, exactly. And you can also see that you can find some that use induction heaters to straighten the deck of a ship, for example. Go around. It looks like a little vacuum cleaner, that sort of moving around, and then to sort of straighten it out.
Okay. Pretty smart. So when you go out and try to bring this to the market, what are the dimensions that you believe in there? Is it these small hand sizes, or are we talking tools for making big components?
We have as part of that project, and we're talking with industries that sort of represent from the very small parts to the medium parts to the very, very, very large parts. We can see that where there's a lot of interest is in the very small parts and in the very large parts. And I think handling and options becomes a big part of that. If you make something that's very, very small, there's fewer options on how to do that. If you make something that's very, very large, there's fewer options on how to do that. And if you make something that's very large, typically everything is manual or semi-manual. So having an automatic way to do that would benefit.
Yeah. So the product, when you go out and install, there must also be a lot of software included in the package. So
Yes.
have you built that yourself?
Yeah. So we have built most of that. Me and a few colleagues have worked on the past many years trying to develop what are the algorithms necessary for doing this. If we want to make a double curve path, you need to decide like where do you want to put the laser, how much heat should you put into it, which paths in which order, how do you deform it then, how do you evaluate it. That's a very complicated process.
I have a last technical question. I think I forgot when we talked about the power input. What level of power are we talking? Is it 500, 800 watt, or where are we?
We typically are in the range of a couple of hundred up to about 800 watts, but that's working in the 1-2 millimeter range thickness.
Okay.
If you want to go thicker, that means you want to defocus more. That means you want to at least have more power available. So that sort of determines how fast can you move forward, how much can you defocus.
Yeah. So the 20 mil blade you talked about, you need a bit more than 800 watt.
Yes, that was 3 kilowatt we put into it.
Yeah, I could imagine that you need a lot more in that perspective.
Yeah.
Wow, Anders, I really like this process. I would like to thank you a lot for sharing. I loved your video, especially the first one showing that it works in real life. Do you have any places where people could go to see more?
Yes, I don't know when this is coming out, but I actually have a colleague who's doing a PhD presentation on Tuesday on his thesis. So if you're quick, that's an announcement. I think it's broadcast online. You can see some of his work on it. But you can also check out Aalborg University. You're very free to come by and see our lasers and parts. And if they're interested in hearing more about it, I think you can, leave my email somewhere.
I will do that. Absolutely. Thank you very much. I'm sure I will be back with more questions. Maybe we can make a new episode when you have reached the next level
That would be very interesting.
and installed the first equipment at a customer. That would
be. I am looking forward to that day.
Yeah, me too. Okay, thank you very much.
Thank you for having me.
Yeah, see you.
Bye bye.